giant skeleton was found chained inside a sealed stone chamber. And at the same time, oceans froze in seconds. The ground swallowed entire neighborhoods, and the sky stopped behaving the way we understand it. Coincidence, or a message we are choosing not to understand? Across the United States, a pattern of events has been unfolding that is difficult to dismiss as isolated or random. These are not singular anomalies that can be neatly categorized and forgotten. They are layered, overlapping, and increasingly synchronized disruptions that are forcing even the most skeptical observers to pause and reconsider their assumptions. Along the historic coastline of Savannah, Georgia, an extreme Arctic air intrusion collided with a high tide system and produced a phenomenon rarely documented in modern meteorological records. Ocean water did not simply freeze over time. It flash froze into jagged, immovable formations that trapped vehicles, damaged infrastructure, and cut power within minutes. Local weather coverage and reports from outlets such as the Weather Channel describe the event as highly unusual due to the speed and intensity of the freezing process. Especially in a region accustomed to humidity and mild winters, rather than sudden polar conditions. While that scene was still being processed by emergency responders, another crisis was unfolding hundreds of miles away in Virginia Beach. Without any prior seismic alerts or visible warning signs, sections of land collapsed into massive sinkholes, swallowing asphalt roads and leaving residential homes dangerously suspended at the edges of newly formed voids. According to the United States Geological Survey, sinkholes typically develop gradually as underground erosion weakens the structural integrity of the soil over extended periods of time. However, the alarming factor in recent incidents is not just their formation, but their sudden visibility and increasing frequency across multiple states along the East Coast. These collapses are not occurring in isolation. They are emerging in clusters, suggesting a broader destabilization beneath the surface that had gone unnoticed until the moment of failure. At nearly the same time, on the opposite side of the country, Lake Oroville in California began exhibiting behavior that defied expected environmental triggers. Known as one of the largest reservoirs in the state, the lake has been closely monitored for years, particularly after previous structural concerns that were widely covered by CNN and the Los Angeles Times. Yet this time, there were no storms, no significant rainfall, and no mechanical breakdowns reported. Despite the absence of these typical factors, water levels began to rise during the night, accompanied by pressure fluctuations that forced local authorities to activate warning systems. Residents described a growing sense of unease as sirens replaced silence, not in response to a visible disaster, but in anticipation of something that could not be clearly defined. Simultaneously, reports from South Carolina, Oklahoma, and Pennsylvania added another layer to the unfolding pattern. In these regions, residents began documenting ground fissures accompanied by deep, rhythmic vibrations that sounded like distant underground thunder. These were not sharp, explosive events, but slow, resonant movements that seemed to build from beneath the surface. In some locations, flames were observed emerging from cracks in frozen ground, creating a visual contradiction that was as unsettling as it was difficult to interpret. Scientists have pointed to methane gas release as a plausible explanation, noting that shifting tectonic pressure can force trapped gases upward where they ignite upon contact with air. This explanation is consistent with known geological processes and has been referenced in environmental studies. However, the timing of these occurrences, particularly their appearance during extreme cold conditions and across multiple states at once, has led many to question whether standard explanations are sufficient. What makes these events especially significant is not the existence of each phenomenon on its own, but the way they are appearing together within a compressed time frame. Extreme cold surges, ground collapses, unexplained water movement, and subterranean gas releases are all recognized within scientific literature. Organizations such as NOAA and USGS have documented each of these processes in detail. Yet historically, they tend to occur independently, influenced by localized environmental conditions. The current situation is different. The overlap suggests a convergence of stress factors affecting multiple systems at once. This raises a critical point that cannot be ignored. When independent variables begin to behave in coordinated ways, the underlying cause may extend beyond what is immediately visible. Data emerging from geological monitoring further reinforces this concern. In Alaska, for example, more than 200 earthquakes were recorded within a 48-hour period, a statistic reported by both USGS and international outlets such as Reuters. While Alaska is no stranger to seismic activity due to its position along the Pacific Ring of Fire, the density and clustering of these events indicate heightened tectonic movement. At the same time, several major volcanoes around the world, including Kilauea in Hawaii, Shiveluch in Russia, and Krakatoa in Indonesia, have shown increased activity. Reports from BBC and Reuters have highlighted this simultaneous escalation, noting that while such activity is not unprecedented, the timing and number of concurrent eruptions are drawing attention from the scientific community. When viewed collectively, these developments form a pattern that challenges conventional interpretation. Infrastructure failures, environmental instability, and geological disturbances are not occurring sequentially, but concurrently. Electrical grids have struggled under sudden temperature shifts. Transportation systems have been disrupted without warning. Communities that once relied on predictable seasonal cycles are now facing conditions that change within hours rather than weeks. The systems designed to support modern life were built on the assumption that natural patterns would remain within a manageable range of variation. That assumption is now being tested in real time. Despite the availability of scientific explanations for individual events, there remains a gap between data and perception. Experts can describe how methane ignites, how sinkholes form, and how atmospheric pressure influences weather systems. These explanations are valid and necessary. However, they do not fully address the broader question of why these events are intensifying together. The distinction between explanation and understanding becomes important here. Explaining a mechanism does not necessarily explain timing, scale, or coordination. This distinction is where uncertainty begins to grow. As more reports surface and more data is analyzed, one conclusion becomes increasingly difficult to avoid. The environment is not behaving in the fragmented way it once did. Instead, it is responding as an interconnected system under pressure. Whether that pressure is driven by climate change, geological cycles, or factors not yet fully understood, the result is the same. Stability is becoming less predictable. The margin for error is shrinking. And the confidence that once defined modern infrastructure and scientific forecasting is being quietly challenged by events that do not follow expected timelines. This is where the narrative shifts from observation to implication. If the ground can give way without warning, if water can rise without cause, and if fire can emerge from frozen earth, then the foundation of certainty itself begins to erode. The question is no longer limited to what is happening in specific locations. It expands into something broader and more difficult to answer. What does it mean when multiple systems begin to fail at once? Not catastrophically, but persistently, and without clear synchronization to known triggers. Scientific explanations have been presented quickly and with confidence, and on the surface, they appear consistent with what we already understand about the natural world. Climate scientists point to shifting atmospheric patterns and the increasing instability of polar air masses as a direct result of long-term climate change. which has been documented extensively by organizations such as the National Oceanic and Atmospheric Administration. According to NOAA, disruptions in the polar vortex can drive extreme cold far beyond its usual boundaries, affecting regions that are not structurally prepared for such conditions. At the same time, civil engineers and geologists highlight the role of aging infrastructure in urban sinkhole formation, noting that decades-old water systems, drainage failures, and underground erosion can weaken the ground until collapse becomes inevitable. The United States Geological Survey has repeatedly emphasized that sinkholes are not sudden anomalies, but the final stage of a long, invisible process occurring beneath the surface. Hydrologists add another layer of explanation by pointing to groundwater pressure fluctuations as a cause of sudden water level changes in reservoirs and lakes, particularly in regions where water management systems interact with natural aquifers. In parallel, geochemists explain the appearance of fire emerging from frozen ground through the release of methane gas, which can accumulate under pressure and ignite when it escapes into the atmosphere. Each of these explanations is grounded in verified scientific principles, supported by decades of research and reinforced by data collected from multiple independent agencies. However, the issue that continues to challenge both experts and the public is not whether these explanations are valid, but whether they are sufficient when considered together. Individually, each phenomenon can be explained within its own scientific framework. Extreme cold can be traced to atmospheric circulation, sinkholes to subsurface erosion, rising water levels to hydrological shifts, and methane fires to geological pressure systems. The difficulty emerges when all of these events occur within the same time frame, across different regions, and without clear causal links between them. Science is highly effective at isolating variables and identifying mechanisms, but it becomes more complex when multiple systems begin to show signs of stress simultaneously. The convergence of independent processes raises the possibility that there may be broader forces at work, or at the very least, interactions between systems that are not yet fully understood. This concern becomes more pronounced when examining recent seismic and volcanic activity. According to data released by the United States Geological Survey, the state of Alaska recorded more than 200 earthquakes within a 48-hour period, a level of activity that, while not entirely unprecedented, indicates a significant increase in tectonic movement. This data has been cited and discussed in reports by international news agencies such as Reuters, which have noted the clustering of these events as a point of interest for geologists monitoring global plate dynamics. At the same time, several major volcanoes around the world have shown heightened activity within overlapping timeframes. Kilauea in Hawaii, Shiveluch in Russia, and Krakatoa in Indonesia have all been identified in reports from BBC and Reuters as experiencing eruptions or increased volcanic output. While each of these locations exists within known tectonic zones, the simultaneity of their activity adds complexity to the overall picture. When seismic activity intensifies in one region, it is often studied as a localized event. When similar patterns appear across multiple regions at once, the interpretation becomes less straightforward. The interaction between geological, atmospheric, and hydrological systems is not a new concept. Earth operates as a complex, interconnected system in which changes in one domain can influence others. However, the scale and timing of current observations suggest a level of synchronization that is difficult to attribute solely to independent processes. If tectonic pressure increases, it can influence volcanic activity. If atmospheric patterns shift, they can affect ocean temperatures and weather systems. These interactions are acknowledged within scientific literature, yet the current situation appears to involve multiple layers of activity occurring in parallel rather than in sequence. This distinction is important because it challenges the predictive models that are typically used to assess risk and prepare responses. At this point, The question shifts from whether science can explain individual mechanisms to whether it can fully account for the broader pattern that is emerging. Scientific understanding is always evolving, and gaps in knowledge are expected in any complex system. The presence of unexplained correlations does not invalidate existing theories, but it does indicate that further investigation is necessary. The concern is not that science is failing, but that the current framework may not yet capture the full scope of interactions taking place. When multiple systems exhibit instability at the same time, it suggests that underlying conditions may be changing in ways that are not immediately visible through standard measurement methods. This leads directly into a different type of interpretation, one that has existed long before modern science began to analyze natural phenomena. In many religious traditions, particularly within the texts of the Bible, large-scale disturbances in nature are described not only as physical events, but as indicators of deeper transitions. In the Gospel of Luke, specifically chapter 21, verses 25 to 26, there is a passage that describes signs appearing in the sun, the moon, and the stars, along with turmoil in the seas and distress among people who do not understand what is happening. This description does not provide a scientific explanation, but it presents a framework in which natural events are connected to human awareness and response. Similarly, the book of Hebrews contains the statement that everything capable of being shaken will be shaken, leaving only what is truly stable. This concept introduces the idea that periods of instability serve to reveal underlying weaknesses, both in physical structures and in systems of belief. When these descriptions are compared with current observations, the similarities are noticeable, but they should be approached with caution. The presence of parallel imagery does not automatically confirm that present events are fulfilling ancient prophecies. What it does suggest is that human societies have long recognized a connection between environmental disruption and moments of transition. Historical texts often frame these disruptions as signals, not necessarily because they predict specific events, but because they reflect an understanding that stability is not permanent. The recurrence of themes such as flooding, fire, ground collapse, and widespread uncertainty indicates that these experiences have been significant enough throughout history to be recorded and interpreted within cultural and religious contexts. In practical terms, the comparison between scientific explanation and religious interpretation highlights two different approaches to the same set of observations. Science focuses on mechanisms, measurements, and predictive models. It seeks to answer how events occur and under what conditions they are likely to repeat. Religion, on the other hand, often addresses meaning, purpose, and human response. It asks why events matter and how individuals and communities should interpret them. These approaches are not mutually exclusive, but they operate on different levels. When scientific explanations leave gaps in understanding, it is common for people to look toward other frameworks that can provide context, even if those frameworks do not offer empirical verification. The current situation, characterized by overlapping environmental disruptions, places both approaches under scrutiny. Scientific institutions continue to gather data, refine models, and develop explanations based on observable evidence. At the same time, the scale and simultaneity of events are prompting broader questions that extend beyond technical analysis. The presence of uncertainty creates space for multiple interpretations, and the challenge lies in distinguishing between what can be measured and what is being inferred. What remains clear is that the environment is undergoing changes that are being experienced directly by populations across multiple regions. These changes are not abstract or theoretical. They affect infrastructure, safety, and daily life. Whether viewed through the lens of science, religion, or a combination of both, the events themselves are real and measurable. The question that follows is not limited to identifying causes, but extends to understanding implications. If current patterns continue, the systems designed to manage risk may need to be re-evaluated. If new interactions between environmental factors are emerging, they will require new methods of analysis and response. At this stage, it is not necessary to reach a definitive conclusion about whether these events carry deeper meaning beyond their physical causes. What is necessary is to acknowledge that the combination of factors being observed is unusual enough to warrant attention. Scientific explanations provide essential insight into how processes work, but they do not always address why multiple processes align in specific ways. Religious texts offer interpretive frameworks, but they do not replace the need for empirical investigation. The intersection of these perspectives creates a space where questions can be asked without immediate answers. As the situation continues to develop, the focus will likely shift toward identifying patterns over longer periods of time. Short-term observations can reveal anomalies, but sustained analysis is required to determine whether these anomalies represent a temporary fluctuation or a more permanent shift. In the meantime, the coexistence of scientific explanation and broader interpretation reflects the complexity of the moment. The environment is not presenting a single, isolated problem. It is presenting a series of interconnected challenges that require both detailed analysis and a willingness to consider perspectives beyond immediate measurement. As the analysis moves beyond large-scale environmental patterns and into more localized observations, a new category of reports begins to emerge, and these reports are significantly more difficult to verify, categorize, or explain within established scientific frameworks. One of the most controversial areas involves accounts of unidentified phenomena that do not fit cleanly into geological or atmospheric models. Along the Mississippi River, multiple fishermen have reported incidents in which heavy-duty nets were torn apart with a force that exceeded what is typically expected from known aquatic wildlife. These are not isolated testimonies from a single location or a single event. Similar descriptions have appeared across different docking points, suggesting that whatever is causing the damage is not confined to a narrow stretch of water. In addition to physical evidence, several dockside camera systems have captured footage showing large, dark shapes moving beneath the surface. What makes these recordings notable is not just the size of the shadows, but the absence of surface disturbance. Under normal conditions, an object of significant mass moving through water would create visible ripples, turbulence, or displacement patterns. In these cases, the movement appears smooth and silent, without the expected interaction with the surrounding water. While there has been no official confirmation from regulatory agencies, references to unusual sonar readings have surfaced in technical discussions, indicating areas of turbulence and motion where water conditions should have remained stable. These sonar anomalies have not been publicly classified as evidence of unknown entities, but they remain unexplained within the context of standard river dynamics. At the same time, attention has shifted toward Yellowstone, a region already known for its geothermal volatility and constant monitoring. Reports compiled from sources such as the National Park Service and coverage by NBC News confirm that animal migration patterns in the area have deviated from expected seasonal behavior. Wildlife movement in Yellowstone is not unusual, and migrations occur regularly in response to environmental cues such as temperature shifts, food availability, and mating cycles. However, the current observations differ in both scale and timing. Multiple species, including bison, elk, and smaller mammals, have been seen moving away from core geothermal zones in a manner that does not align with documented patterns from previous years. What intensifies the concern is the lack of corresponding data from seismic instruments. Typically, unusual animal behavior in Yellowstone has been associated with measurable geological activity such as increased tremors, gas emissions, or changes in ground temperature. In this instance, monitoring systems have not recorded anomalies of sufficient magnitude to explain the widespread behavioral shift. This discrepancy creates a critical gap between biological response and instrumental measurement. Animals are known to possess heightened sensitivity to environmental changes, including vibrations, electromagnetic fluctuations, and chemical signals that humans cannot detect without specialized equipment. There is a substantial body of research supporting the idea that certain species can perceive early indicators of earthquakes or volcanic activity before those indicators become measurable through conventional sensors. However, when animal behavior suggests the presence of a disturbance that instruments fail to detect, it introduces a level of uncertainty that cannot be easily resolved. Either the instruments are not capturing the full range of relevant signals, or the animals are responding to stimuli that are not yet fully understood within scientific models. This situation highlights a broader limitation in the way environmental data is collected and interpreted. Modern monitoring systems rely on specific parameters such as seismic waves, temperature gradients, gas concentrations, and pressure changes. These parameters are effective for identifying known processes, but they may not account for subtle or emerging variables that fall outside established detection thresholds. If there are environmental changes occurring at frequencies, scales, or intensities that current instruments are not designed to measure, then those changes would remain effectively invisible to standard analysis. In contrast, biological systems, which have evolved over long periods to respond to complex environmental signals, may detect these changes through mechanisms that are not yet fully understood or replicated technologically. The combination of unexplained sonar readings in major river systems and uncharacteristic wildlife movement in highly monitored regions suggests that there are elements within the current pattern of events that extend beyond conventional explanation. It is important to approach these observations with caution and avoid premature conclusions. Anecdotal reports, even when supported by partial data, do not constitute definitive evidence of unknown phenomena. At the same time, dismissing these reports entirely would overlook potentially valuable indicators of underlying processes that have not yet been identified. As the sequence of events continues to develop, these localized anomalies begin to serve a different role within the broader narrative. They are no longer isolated curiosities, but components of a larger system that appears to be under stress. Large-scale environmental disruptions establish the context, while smaller, harder-to-explain observations introduce complexity and challenge existing assumptions. When both levels of activity occur simultaneously, the overall picture becomes more difficult to interpret using a single framework. The logical progression from here leads toward a critical escalation in both scope and intensity. If unexplained anomalies at the local level are appearing alongside measurable disruptions at the global level, then the possibility of a converging pattern becomes more relevant. This does not imply a single cause or a unified mechanism, but it does suggest that multiple systems may be reaching points of instability at the same time. The next stage of analysis must therefore move beyond individual observations and begin to examine whether these events, both explained and unexplained, are part of a larger synchronization that is only now becoming visible. As the sequence of observations expands from isolated anomalies into broader data sets, the most critical development is no longer any single event, but the pattern that emerges when all of them are viewed together. The concern reaches its highest point when independent systems begin to show signs of stress within the same narrow time frame, creating what can only be described as a convergence. According to compiled reports from organizations such as the United States Geological Survey and coverage by international outlets, including Reuters, there has been a measurable increase in seismic activity, volcanic eruptions, extreme weather events, and hydrological instability occurring across multiple regions at nearly the same time. This is not limited to the United States. In Turkey, for example, cities such as Trabzon and Elazig experienced snowfall levels that exceeded historical records, as reported by Anadolu Agency, resulting in infrastructure paralysis and widespread disruption. These events are geographically distant and governed by different environmental systems, yet they are unfolding in parallel rather than in isolation. When fire in the form of volcanic eruptions intensifies, when water systems display irregular behavior, when land becomes unstable through seismic and structural shifts, and when atmospheric conditions produce extreme and unpredictable weather, the combined effect cannot be easily attributed to coincidence. Each of these domains is typically studied independently, with its own set of variables and predictive models. However, when all four primary elements of the natural environment begin to exhibit instability within the same window of time, the statistical likelihood of pure randomness becomes increasingly difficult to defend. What emerges instead is the image of a system under simultaneous pressure from multiple directions. A system that is beginning to reveal points of weakness that were previously hidden beneath layers of apparent stability. This convergence does not necessarily indicate a single cause or a unified trigger, but it does suggest that multiple stress factors may be interacting in ways that amplify their combined impact. In complex systems theory, such behavior is often associated with thresholds, where incremental changes accumulate until a tipping point is reached, resulting in a cascade of visible effects. The current global pattern aligns with this concept. Individual systems that once operated within predictable limits are now showing signs of deviation, and those deviations are occurring in coordination rather than in sequence. This coordination is what transforms a series of anomalies into a potential systemic shift, expanding beyond the immediate data. The implications of this pattern extend into the foundational assumptions that support modern society. For decades, infrastructure, economic systems, and technological networks have been built on the expectation that natural conditions, while variable, would remain within a manageable range. Electrical grids are designed based on temperature averages and predictable demand cycles. Transportation networks rely on stable ground conditions and consistent weather patterns. Water management systems are calibrated to historical rainfall and runoff data. These systems function effectively as long as the underlying assumptions remain valid. When those assumptions begin to fail, even partially, the reliability of the systems built upon them is compromised. Recent observations indicate that this process may already be underway. Power outages caused by unexpected temperature extremes have affected millions of people. Transportation routes have been disrupted not only by severe weather, but by sudden structural failures in the ground itself. Water systems have shown variability that challenges existing management strategies. These are not isolated failures caused by singular events. They are indicators of a broader shift in baseline conditions. Experts from NASA and NOAA have repeatedly warned about the increasing frequency and intensity of extreme weather due to climate change, and their models have successfully predicted many long-term trends. However, even the most advanced simulations have limitations, particularly when it comes to capturing the synchronized behavior of multiple systems across different domains. This gap between prediction and observation forces a reassessment of how environmental data is interpreted. It is no longer sufficient to analyze individual variables in isolation. A more integrated approach is required, one that considers the interactions between atmospheric, geological, and hydrological processes as components of a single dynamic system. The challenge lies in the complexity of these interactions. Each system operates on different timescales and is influenced by a unique set of factors. Bringing them together into a unified model requires not only more data, but new methods of analysis that can account for non-linear relationships and feedback loops. At the same time, the human dimension of this situation cannot be ignored. The sense of stability that has defined modern life is not only a physical condition, but also a psychological one. People make decisions, build communities, and plan for the future based on the expectation that the environment will behave within known parameters. When those parameters become uncertain, the impact extends beyond infrastructure and into perception, confidence, and behavior. The feeling of unpredictability can influence everything from economic activity to public health, as individuals and institutions struggle to adapt to conditions that change faster than established systems can respond. This leads to a broader question about the limits of current understanding. Scientific progress has provided detailed insight into individual processes, but the integration of those processes into a comprehensive framework remains a work in progress. The events being observed are not necessarily beyond explanation, but they may exist at the edge of what current models can accurately describe. This does not imply a failure of science, but rather an opportunity for expansion. New data, new methodologies, and new perspectives will be required to fully understand the scope of what is happening. Within this context, the role of interpretation becomes more significant. When data alone does not provide complete clarity, questions begin to emerge that extend beyond measurement. If multiple systems are changing at once, is it the result of cumulative factors reaching a critical point? Or does it indicate a shift in underlying conditions that has not yet been fully identified? If established models can explain individual components, but not the timing of their convergence, what additional variables need to be considered? These questions do not undermine existing knowledge. Instead, they highlight the need for continued investigation and a willingness to adapt frameworks as new information becomes available. At this stage, it becomes necessary to engage directly with the uncertainty rather than attempting to resolve it prematurely. The presence of unanswered questions is not a weakness, but a reflection of the complexity of the system being studied. The key is to distinguish between what is known, what is inferred, and what remains unknown. Known factors include documented increases in extreme weather, seismic activity, and environmental variability. Inferred connections involve the relationships between these factors and their potential interactions. Unknown elements represent the areas where data is incomplete or where existing models do not fully align with observed patterns. From this perspective, the situation can be understood as a transitional phase in both environmental conditions and human understanding. Transitional phases are characterized by instability, not because systems are failing completely, but because they are adjusting to new conditions. During such phases, variability increases, predictability decreases, and the range of possible outcomes expands. This is consistent with what is currently being observed across multiple domains. The next logical step is not to draw definitive conclusions, but to refine the questions being asked. Instead of focusing solely on whether individual events can be explained, the focus shifts to how those events relate to each other and what that relationship reveals about the system as a whole. This requires a shift in perspective from isolated analysis to integrated observation. It also requires patience, as patterns that appear unclear in the short term may become more defined over longer periods of time. As this process continues, one point remains clear. The environment is not static, and the conditions that once defined stability are subject to change. Whether those changes are gradual or accelerated, localized or widespread, predictable or unexpected, they have direct implications for the systems that depend on them. Recognizing this reality is the first step toward adapting to it. This brings the discussion to a point where direct questions must be considered. If all of these events were purely random, what explains their timing and their overlap? If scientific models can account for individual mechanisms, why does the combined pattern still generate uncertainty? If historical records, whether scientific or cultural, contain descriptions of similar conditions, what can be learned from those parallels without assuming direct equivalence? These questions are not rhetorical. They are central to understanding the current situation and determining how to respond to it. It is possible that future research will provide clear answers that align all of these observations within a single, comprehensive framework. Advances in data collection, modeling, and analysis may reveal connections that are not currently visible. It is also possible that the system itself is undergoing changes that will redefine what is considered normal, requiring continuous adaptation rather than a single explanatory model. Both possibilities remain open, and both require careful attention. In the meantime, the most responsible approach is to remain attentive to both data and context. Observations should be documented, patterns should be analyzed, and conclusions should be drawn based on evidence rather than assumption. At the same time, the broader implications of these observations should not be overlooked. The interaction between environmental conditions and human systems is complex, and changes in one inevitably affect the other. As the situation continues to unfold, the focus will remain on identifying patterns, refining models, and expanding understanding. There is no immediate need to assign definitive meaning to every observation, but there is a clear need to acknowledge that the current pattern differs from what has been observed in the past. That difference is what justifies continued attention and investigation. Ultimately, the question is not limited to whether these events are natural or unusual, expected or unexpected. The question is whether the current framework of understanding is sufficient to interpret what is being observed. And if not, what adjustments are necessary to improve that understanding? The answer to that question will determine how effectively future developments are managed. At this point, one final consideration remains. Regardless of the explanations that emerge, the observable reality is that conditions are changing, and those changes are being experienced directly. The implications of that reality extend beyond theory and into practical decision-making. Preparing for variability, strengthening resilience, and maintaining flexibility in response strategies are all essential components of adapting to uncertain conditions. With that in mind, a simple but important question remains open. Are these events simply a series of independent natural occurrences that happen to align in time? Or are they indicators of a broader shift that requires a reassessment of how the world is understood and how future stability is defined? Please let me know your thoughts in the comments. If you found this video even a little interesting, I would truly appreciate it if you could give it a like and subscribe to the channel. Thank you very much for watching until the end.